Welcome back in the beginning of the college trigonometry lessons. Our first couple of lessons are actually almost all of the lessons for college trigonometry. If you've had me for geometry and algebra 2, we have pretty much covered everything that we've covered in those years. You're just going to be covering in a little bit more detail this year. So again, a lot of this will be review. Just because it does look like review does not mean to slack off on the practice problems on the homework. It's been over a year since you've probably used some of this information. So bear with me and we'll get through some basic items. First thing I want to cover is our Cartesian coordinate plane. Typically, we'll be using the Cartesian coordinate plane. And later on in the semester, we will talk about polar coordinates. So first thing I want to talk about are the quadrants. The quadrants are numbered. In the positive x, positive y quadrant is quadrant 1, and we go counterclockwise for the other three quadrants. So quadrant 1, 2, 3, and 4. Here, x's are positive. Y's are positive above the x-axis, x's are negative to the left, and y's are negative going down. In geometry, our definition of an angle was the intersection of two rays. So for geometry, the definition of an angle would have been the intersection of ray OP with ray OA. Okay, so for geometry, it's two rays. And remember, in geometry class, the measure of any angle was between 0 degrees and 180 degrees. There was no such thing as a 0-degree angle because that would be coincident rays, and had to be less than or equal to 180 degrees, and that would have been formed by what was called opposite rays, and another name for that one, which was 180 degrees, was a straight angle. And then in the second semester of geometry, when we started talking about circles, we started going above the 180 degrees, and that's where we introduced the definition that we will use for an angle. And our new definition of an angle is we will start with an initial side, and we will rotate around a fixed point. We're not going to draw a second ray. What you need to think about here is that we're just physically going to rotate this ray into a new position. And that amount that we rotated the ray is the angle that is formed. We typically use Greek letters like theta to indicate angles. Okay? This is the initial side, and where it stops, they call this the terminal side. Okay? Again, just like my geometric interpretation, this is a vertex of the angle here where the two rays intersect, and the fixed point of rotation in my trigonometric view of an angle is where the vertex of the angle is. An angle is in standard position, so any angle I have is in standard position is if its initial side lies along the positive x-axis. So any angle is in standard position if its initial side is on the positive x-axis. And I can rotate in either direction. If I rotate counterclockwise, I'm going to go positive. That's what's considered a positive rotation. And if I rotate clockwise, it's considered a negative rotation. And an entire revolution is 360 degrees. And if I do a revolution in the other direction, I would call that one negative 360 degrees. There are an infinite number of angles that can have the same terminal side. So, if I draw an angle in standard position, and I'm just going to draw a 45-degree angle. That's one angle that has this as its terminal side. I'm going to put terminal up here. I have another one that's negative 180. Negative 270 plus 45 would be negative 315 degrees. Or I can rotate all the way around again and come back up here, and that would be 405 degrees. Or I can continue rotating around again, and that would be 765 degrees. So again, there's an infinite number of what they're calling coterminal angles, angles that are in standard position that have the same terminal side. And the way that you get coterminal angles is you just either add or subtract multiples of 360 from your original angle. You want to add or subtract an entire circle. So if I want to know if two angles are coterminal, for example, 810 degrees and let's go 650 degrees, all I have to do is subtract them, one from the other. So 0, that's a 7, that's a 1, that's a 6. And is that divisible evenly by 360? No, it's not, so they cannot be coterminal. So that's one easy way you can tell whether or not angles are coterminal. So the next thing that we're going to cover is radian measurements of angles. So the same thing applies for angles that have radians as their unit. Still have coterminal angles. So next formula will be very important for us. And it tells me that if I have a circle with a radius of r, and I rotate that radius so that it follows a certain arc length, which we are going to call S, I will have a given angle right here, and the relationship is that S is equal to r theta, or if I rearrange that, I know that theta is equal to S over r. S is a distance, okay? 5 feet, 10 feet, okay? Going around here. And because it's in regards to the radius of a circle, well, what's the distance all the way around a circle called? Well, it's called its circumference. And we know the circumference is 2 pi r. Well, let's say I rotated all the way around the circle. That would be my S. Well, what's my radius? Well, it's r. So if I want to know what theta is, for an entire revolution, I would take the 2 pi r for the circumference, which is my big arc length, divide it by the radius, and that tells me that a full revolution is going to give me 2 pi radians. Okay? In Algebra 2, we made you copy the unit circle and show where all the different radian measures were. You should get back into practice doing that. So what I'm going to do now is I'm just going to redraw the coordinate plane. I'm going to leave these two formulas up here because we're going to use them for some problems. But redraw the coordinate plane. I'm going to draw a circle. And besides going, if this is 2 pi all the way around, we know it's pi here. Okay, this would be 2 pi. That's 0. Well, that would be half of a pi. So it would be 1.5 pi's. Okay, that's one representation of it. That's when we actually have pi that's still in there that hasn't been put through. Well, where I found that students are having issues is if I just give you numbers, for example, 2. If the measurement is 2, where would that fall in the coordinate plane? Well, pi is almost 3. So I'm going to call that 3. Okay? That's about 1.7. So I know 2 is going to be about here. And that would put 1 here. Okay, and then, see, 1.7 plus 3.4 is 5.1, so this is going to be 5, probably a lot narrower here. So 4 is going to be halfway in between the two of them. And that would give me 6 pi over here, and that's 6.28 pi. So you can see, if I have 1 radian, I'm in the first quadrant. 2 and 3 radians, I'm in the second quadrant. 4 and 5 radians, I'm here, and then 6 radians. So just because we have pi's in there, don't forget that, hey, if you were to multiply this out, yes, you'd have to round it off. 3 times 3.14 divided by 2, which would be 3 times 1 point something. And be able to figure out where you are there. So don't lose the fact that you can turn those pi's into numbers. Okay. So other things we need to talk about with regards to angles before we start using these formulas are complements and supplements. Okay. Complements add up to 90 degrees. These are 2 angles. And supplements are 2 angles that add up to 180 degrees. Okay. Well, 90 degrees in radians is pi half. And 180 degrees in radians is pi. So you're going to need to be able to find complements and supplements both in radian form and decimal form. Other fact I want to put up here is that we know that 1 pi is 180 degrees. Okay, pi radians. Okay, we won't write the unit because radians is the most often used angle measurement once you get above general math. So any calculus, you don't use degrees at all, you use radians. So pi radians is equivalent to 180 degrees. That's just like the same thing as saying 3 feet is equal to 1 yard. I'm not saying that 3.14 is equal to 180, but pi radians is 180 degrees. Well, we can just take half of that side and take half of that side, and that gives me pi halves is equal to 90 degrees. Okay? Or I can take a quarter of that side and a quarter of that side, and that tells me that pi fourths is equal to 45 degrees. So one way I can do that to come up with quick relationships of what the fractional forms of my radians are. A lot of students don't do that, but they do know. Let's say I wanted to convert, we'll say 2.3 radians is equal to how many degrees? Well, what you do is, well, we just set up our proportion. Well, radians over radians, to get those to cancel. Well, how many radians are in a whole circle? 2 pi. Well, how many degrees are in a whole circle? 360. And you would end up multiplying both sides by 360. Okay? So those cancel. The radians will cancel. Stick that into your calculator. So 2.3 times 360 divided by 2 divided by pi. It's 131.78 approximately. Well, let's see, 2.3. 2.3, somewhere in here. Well, that's 90. Yep. It looks pretty good. And you can use the same thing converting from degrees into radians. For example, if I tell you that I have negative 124 degrees, and I want to know how many radians, well, how many degrees are there in a whole circle? 360. How many radians are there in a whole circle? 2 pi. Now I need to solve for my x. I'm going to multiply both sides by 2 pi. And I get 2 pi times negative 124 equals, divided by 360 equals approximately negative 2.16 radians. So the rest that I'm going to cover is just some sample problems very similar to your homework. And with that, we will be able to get the homework done for our first section. So the first types of questions I'm asking you is to draw angles in standard position. And then we're going to want to find positive and negative coterminal angles for them. So I am going to do the following: 485 degrees, negative 320 degrees, 7 pi 11ths, negative 3 pi 8ths. So, first thing I want to do is I want to sketch. Then I want to find a positive coterminal and a negative coterminal angle for each one of those. So, when I sketch the angle, all of these will be sketched in standard position, so I don't need you to show me this initial side, but I do need you to show me how you're rotating. So, because that's positive, I'm going to rotate counterclockwise. That's more than 360, so I know I'm going to go all the way around. Another 90 is 450 plus 35 more degrees. Then label it with how much it was. So that's how you would do the first part of that question. The next thing is to find another angle that's positive that's coterminal to this one. Well, I can either add or subtract 360 degrees from it. So I'm going to subtract 360 and get 125 degrees. And I want a negative coterminal angle, so I'll subtract another 360 degrees. I'm going to do 125 minus 360 is negative 235 degrees. Again, I need to show my rotation. This is negative, so it's clockwise. So that's 270 plus 50 more. Negative 320 degrees. I need a positive coterminal angle, so I'm going to add 360 to that and get 40 degrees. I need a negative coterminal angle, so I'm going to subtract 360 from that one and get negative 680 degrees. Now, two examples in radians, 7 pi 11ths. Well, that would be 5.5 11ths. That would be 11 11ths. So 7 pi 11ths is somewhere in quadrant 2. And we write 7 pi 11ths. I want another positive coterminal angle, so I'm going to add 2 pi to that. 2 pi is 22 11ths. So that would be 29 11ths. And I'm going to subtract 22 11ths from that and get negative 15 11ths, or by 2 coterminal angles. And the next example, well, this is negative 1. This is negative a half. Well, negative 3/8, so that would be negative 4/8. So negative 3/8 is 3/4 of that. Two pi for a full revolution to get back here from the positive side would be 16. It would be 16/8. So 16 minus 3 would be 13/8 of a pi. Subtract 16/8 from that, and I get negative 19/8 pi. So that's the first type of homework problems you have. I've already showed you examples of doing radians to degrees and degrees to radians. Next examples I'm going to do are finding complements and supplements in both degrees and radian mode. So the two angles I'm going to use are 55 degrees and 5 pi 12ths. The complement is what angle added to this gives me 90 degrees. So it would be 90 minus 55, which is 45. The supplement is 180 minus 55 equals 125, 130. 125. For 5 pi 12ths, I want to know pi, because 90 degrees is pi, which is 12 12ths pi minus 5 12ths pi is 7 12ths pi. Except I wanted pi halves, so I did the other one first. So that would be 6 minus 5 is 1. So complement is pi halves, 90 degrees. Supplement is a full pi, so 12 12ths pi minus 5 12ths pi is 7 12ths pi. Next type of questions are if I give you a radius and an angle measurement, find the arc length, and you should be able to use any portion of those types of problems. If I give you any two of the three. So the relationship again we have is S is equal to R theta. My first example is I want to know the arc length if the radius is 9 feet and theta is equal to 60 degrees. The second one is radius is equal to 20 centimeters. And actually get to the homework problem because it's illegible in my piece of paper. Pi-4 radians. The second one is actually the easier one to do because this is the definition based off of it being in radians. Well, so if it's in radians, all I have to do is go r times theta. Well, what's 20 centimeters times pi fourths? That would cancel, and my answer would be 5 pi, would be the arc length. If it's in degrees, you have to think about what the arc length actually means. The arc length is a portion of a circle. So how far is it all the way around a circle? Well, it's 2 pi r times the fraction of the circle that you went around. Well, what fraction did I go around? I did 60 over 360. 60 goes into both of those, 1 over 6 times. My radius is 9, so I'm going to rewrite this as 2 times pi times 9 over 6. I'm going to take a 2 out of here, a 3 out of here. That gets rid of that 6, so I get 3 pi. And that unit would be feet. So if you don't remember this formula, the easiest way to remember arc length is, hey, it's just a fraction of the circumference. Write the circumference and multiply it by a fraction. Write the circumference and multiply it by a fraction. The next type of problem I want to get to is like one of your homework problems, and it is they give you two positions. They give you the latitude of San Francisco and Seattle. So basically what they're telling you is, hey, on the Earth, which has a radius of, they're giving you 4,000 miles, they tell you that San Francisco is located at 37 degrees, 47 minutes, and 36 seconds north. And Seattle is located at 47 degrees, 37 minutes, and 18 seconds north. And it wants to know how far it is between the two of them. They tell you that they're on the same longitude line, so they're directly north and south of each. Seattle's directly north of San Francisco, so we don't have to worry about weirdness with the radius of the Earth. Well, this is just an S equals R theta type problem. Well, this is something you may not have seen, are the minutes and seconds with that, and they're just like they are minutes and seconds when we're dealing with hours. Well, a minute is a 60th of a degree, and a second is a 3600th of a degree. So what I'm going to do is I'm going to do the conversion and turn everything into fractional degrees. And then I'm going to subtract San Francisco from Seattle, and that will tell me how many degrees apart they are. And then I can do the 2 pi r times a fraction. So 47 plus 37 60ths plus 18 3600ths. That's 47.6217. Then I can do 37 plus 47 60ths plus 36 3600ths. That's 37.7933. I'm going to do 47.6217 minus 37.7933, approximately 9.8284 degrees. That's 8284. So 9.8284 degrees. Well, I want to know how far apart they are. Well, it's S equals R. Well, I'm not in radians, so I can convert it to radians and use that formula. Or I can know that it's 2 times pi times the radius times how far I went around out of a whole circle. So 2 times pi times 4,000. That's miles, is our unit. Times 9.8284 equals, divided by 360 equals, and I get approximately 686.15 miles. So that's how doing these things can you can use latitudes and longitudes to find distances in between 2 points. 2 other types of problems I need to do. One is to find the area of a sector. To find the area of a sector, the way I want you to do it is you're going to find the area of a whole circle and multiply it by a fraction. So the 2 examples I'm going to do are ones in radians. So I have a radius of 12 millimeters and a theta of 5/4. And then the second example is 1.4 miles and an angle of 330 degrees. So what this is saying, pi fourths would be that angle. They want to know what that area is. Well, it's the area of a circle, which is pi times radius squared times a fraction. Well, it's pi fourths divided by 2 pi. On a problem like this one that's in radians, I'd want you to give me the exact answer. The pi's cancel. Those pi's cancel. So I'm left with 144 pi millimeters squared over 8. 8 goes into both of these. 8 goes into 14 once, with 6 left over. 8 goes into 64 8. And don't forget, units of area are squared units. The other example, pi times 1.4 miles squared times 330 over 360. I'd go ahead and let you use a calculator on this one. I would cheat. I would rewrite this as 14 over 10 squared and try to come up with an exact answer. But we're going to use the calculator, so I have pi times 14 squared times 330 divided by 360. And get approximately 564.44 miles. That does not sound right. I did 14 squared, not 1.4 squared. So let's go 1 point square. Pi times 1.4 squared times 300 divided by 360. There was no way I was going to get 500 miles out of something with that radius. How about 5.13 miles? And the last example I want to do is homework problem number 107. And it says, a satellite is on a circular orbit 1,250 kilometers above the Earth. So I'm going to draw a picture. I've got my nice little satellite that is 1,250 kilometers above the Earth. It does one revolution every 110 minutes. 110 minutes per revolution. Assume that the Earth is a sphere with a radius of 6,378 kilometers. And it is asking you to find its linear speed. Linear speed is going to be a distance over amount of time. Okay? Well, what you need to realize is, hey, this is really important because this is actually rotating about the center of the Earth. So the entire radius of the arc that is swinging out is the 6,378 plus the 1,250. So I'm going to draw it on a little different scale here. There's my radius, which is going to be 8, 12, 6, 7. I better use a calculator to check that. 76, 6,378 plus 1,250. Yep. 7628 kilometers is the radius. So we're going to start here. Okay? What I want to do is I want to get a distance over a time. Well, this is a time over revolution. So I'm going to flip that thing over. So I'm going to write one revolution in 110 minutes. Well, how far around does it go in one revolution? It goes its circumference. Well, it goes 2 times pi times 7628 kilometers per revolution. And they want it in kilometers per minute. And do I have that for my units now? Revolutions cancel. Approximately, because I'm rounding in a calculator and I got pi's. So 2 times pi, so do the circumference, divided by how long it takes to go around once. So 2 pi times 7628 divided by 110. It's approximately 435.7 kilometers per minute. I could ask the same thing. What is its angular velocity? Well, an angular velocity is how many degrees or how many radians does it go per revolution? Well, so this is my linear velocity. Well, angular velocity, I'm going to use the same information. I do one revolution in 110 minutes. Well, how many radians is there per revolution? Well, there is 2 pi radians per revolution. And I do 2 pi radians in 110 minutes. So that'll tell me how many radians per minute. So 2 pi divided by 110 is approximately 0.057 radians per minute. And this would be angular velocity. So I should have done enough example problems that I've done at least one of every single type of homework problem that you have. Again, we've done pretty much all of this before, maybe not the angular velocity, linear velocities, and converting degrees, minutes, seconds to degrees, but the rest of this work you have seen before.